Hi Math 215 students. In this video we're going to be talking about one-to-one and onto transformations. The outcomes for this video are as shown here. At the end of it you want to be able to describe what an onto mapping is and what a one-to-one mapping is, and decide whether a given linear transformation is one or the other, or both. So we're going to back up just a little bit. You'll remember that at the first video of this section we talked about functions, and the definitions we're going to talk about today mainly have to do with functions, not so much just with matrix or linear transformations, but that will be the context in which we see them in this class. So to review, a matrix transformation is a vector function having the form where the transformation is given by A times the vector x. And a linear transformation is any transformation that satisfies these two properties. The transformation distributes over addition, and you can factor a scalar multiple outside from a single vector. So as we've seen in the earlier videos, all matrix transformations are linear transformations, and every linear transformation can be written as a matrix transformation using its standard matrix. Now here's the picture we showed when we first talked about functions. Remember, a function is a rule that assigns an output to each input, and our matrix transformations certainly satisfy that property. We asked at the beginning what the domain of this particular matrix transformation was, and we saw that it was R2 because matrix multiplication requires two entries in that vector. And then we asked what is the range, and we saw that the outputs belong to R3, so the range is a subset of R3. It may not be the whole thing, but it does belong to R3. So now we're going to ask two questions that we'll answer in this video. Can two different inputs yield the same output? Now you know that for a function, a single input can only output a single input can only give you a single output. But it is possible in general for two different inputs to give you the same output. If you think about the function x squared, for instance, minus 2 squared is the same thing as positive 2 squared. And so we want to ask if the same thing can happen for matrix transformations. We also want to ask, is there anything in the codomain that is not in the range? Now in this picture, the range is displayed as sort of a hyperplane passing through the codomain, but it is possible, and you might wonder whether a matrix transformation can fill up the entire codomain with its range. So we're going to talk about that second question first. We will say that a mapping from Rn to Rm is onto if each vector in the codomain is the image of at least one vector in the domain. In other words, T is an onto mapping if every point of the codomain actually happens when you plug in all the points from the domain. So this picture, of course, does not display an onto mapping because the range is pictured as just a subset of the codomain, and we want an onto mapping to have a range that fills the entire codomain. So let's take a look at our matrix transformation, and let's decide whether it is an onto mapping. Well, in order to do this, let's remember what onto means. Each vector in the codomain needs to be the image of at least one vector from the domain. So what we're going to do is take a generic entry from the codomain. We'll represent that with B1, B2, B3 here. And we're just going to ask, does this matrix equation always have a solution? Is there always an input vector x that will produce this generic output vector, no matter what the entries b sub 1, b sub 2, b sub 3 are? Well, we're going to try to solve this. We'll do it by row reducing like we normally do. And we'll skip over a few of the details, but hopefully you'll be able to kind of figure out how we arranged our row operations to produce this matrix. And this is the augmented matrix, and you can see that actually we will be in trouble. There will be no solution if this entry here is not 0. If this entry is non-zero, then you'll have no solution because there would be a pivot position in the last column. So, as one example, 1, 1, 0, if B1 was 1, B2 was 1, and 0 was B3, this would end up being non-zero, and so 1, 1, 0 cannot be in the range, and so the function is not an onto function. All right, we've talked about what it means for a function to be an onto function. Now let's talk about what it means for it to be one-to-one. We'll say that a mapping is one-to-one if every two different inputs are mapped to different outputs. So in other words, for any possible output B, there's only one, if any at all, there's only one solution that gets mapped where X gets mapped to B. So the terminology one-to-one is meant to distinguish a mapping where you might have two different things sent to the same one output. That can't happen for a one-to-one function. So this function, t of x1, x2, x3, is defined by x1, 0, and x2 plus x3, is not a one-to-one map, because if I plug in 1, 1, 1, I'll get 1, 0, 2 out. And if I plug in 1, 4, minus 2, I'll get the same output of 1, 0, 2. So we have different inputs yielding the same output, and that is what's forbidden for a one-to-one map. Okay, let's take a look at our matrix transformation and decide whether that is a one-to-one mapping. So what we're going to do is decide whether two or more solutions are possible given an output vector. So what we'll do is we'll take our same generic output vector from before, and we're going to ask whether this equation has more than one solution, or if it ever could have more than one solution. So from row reducing, earlier we saw that you can get to this form here. Now the question is, can you get more than one solution? And as we take a look here, remember the last column corresponds to the right-hand side, but the first two columns, which correspond to x1 and x2, these are pivot columns. There is a pivot position in the first column and in the second column, so neither one is a free variable, and neither x1 nor x2 is free. And so if there is a solution, if this bottom row turns out to be 0, then there would be only one solution. So yes, the function is one-to-one. All right, so in this picture, as we've indicated, this illustrates a non-onto function, but it is a one-to-one function. So we've talked about the two different types of mappings that we'll want to keep with us as we discuss vector transformations, but you have to wonder, is there an easier way to decide, or a more direct way to decide, if a matrix function is one-to-one or onto? Is there something about the matrix that can tell you? And the answer is yes. Now, we're going to talk first about one-to-one functions. So we'll say that a function t is a one-to-one if and only if, and now this is assuming t is a linear transformation, but if t is a linear transformation, t is one-to-one if and only if the vector equation, or the linear transformation equation, t of x is equal to 0, has only the trivial solution. So you'll remember from our definition of one-to-one, we had to worry about whether there was ever two x's that gave you the same vector b, and now this theorem is saying you don't have to work with the generic b necessarily. You can work specifically with the 0 vector and decide whether there are two solutions in that case. Now, for the second theorem, we have a statement about matrix transformations. We'll talk about whether things are one-to-one or onto, and maybe as you take a look at these blanks, you can already see what the answer should be. If t is a linear transformation represented by a, x, and the columns of A are linearly independent, let's remember what that means. If the columns are linearly independent, that means that each one cannot necessarily be expressed as a linear combination of the others. And what that kind of refers to is the fact that you'll never be able to zero out any of the columns by with the other columns. And so that kind of sounds more like our one-to-one criterion. And if the columns of A span Rm, then that means that as you take every possible linear combination of the columns of A, or in other words, as you input every possible vector, your range will end up spanning all of Rm. Your range will be the same as the codomain. You'll have an onto function. And that's exactly what these theorems say, and give you a criterion for deciding whether T is one-to-one or onto, using properties of the matrix that we've already talked about. All right, so now to illustrate that first theorem, T is a linear transformation. T is one-to-one if and only if Tx equals 0 has only the trivial solution. And as you can see here, as we row reduce this matrix, we've put the 0 column in that last column. And as we row reduce, we see that there is only one solution, x1 equals 0, x2 equals 0. So T of x equals 0 has only the trivial solution, and so the matrix is one-to-one. We've talked about what it means for a function to be onto, what it means for a transformation to be one-to-one, and we've illustrated different ways you can decide whether linear transformation is one-to-one and or onto. Thanks for watching. I'll see you in the next video.